Okay, so let me share my screen. I hope you can see my screen, guys. Yeah, thanks a lot. Okay, so let's start. Then here it is. Okay, so the example today is about synchronous reluctance machine. We are going to start from some specification. First, initial sizing to find the diameter, the length of the machine that we need to have, the number of turns, and so on. And then we have to fix the number of poles and the number of slots and make some tests. We are going to test two configuration, and we'll see how to choose the best of the two configuration. Okay, so we have only the specification for this motor, mainly the maximum voltage of the supply. There is no information on the current supply here. We want 75 kilowatt for 2000 RPM, and we need this machine to run time to time at maximum speed of 3000 RPM. The ambient temperature here will be 40 degrees Celsius. So the first thing we need to do here is to compute and check the drive specification. This will help us also to later on to compute the number of turns, and for flex motor to know the settings or the inputs we need for the drive. Okay, so the specification said that we have DC voltage of 600 volt. In flex motor, there is all this inverter control strategy, right? So we have to choose one of them. Here, for this machine, I choose the 6-step 180 degree. So this DC voltage will give us phase-to-phase voltage through this coefficient, root square of 6 divided by P. And then once we choose the inverter control strategy, actually this kind of inverter control strategy, it makes sense to make some preliminary analysis thanks to PSIM in order to choose the right control strategy. Within PSIM, you can have an equivalent model of the motor and try the best one for your motor. Okay, so here I must confess that I took this one. There is no specific reason why I took this one. I took it like this because I have to choose one. Then once we computed the phase-to-phase voltage, we have to take into account let's say the voltage drop in the power electronics, the rectifier. So this is a coefficient of 0.9. Yeah, it can be more or less this value. This is what we use to see actually. But as a preliminary computation, it is enough to put to take 0.9. Okay, so then the voltage, face-to-face voltage, we are going to obtain from this coefficient. We have to multiply it by 0.9, and this is the face-to-face voltage that we are going to consider. Then, once we had that, we need to compute the current, the maximum current for the working point we had. So then we have from the specification, we have this power, the output power. So then if we suppose an efficiency of 0.9%, which is largely possible for this machine. And if we choose a power factor of 0.75, this is something typical for this kind of machine. Remember, this is what we told, and we said previously that this kind of machine suffer from the inductive part, and this is something will degrade the power factor. That's why we usually limit the number of poles of this machine, because to limit the inductance and to limit the reactive power. Okay, so then imposing this efficiency, we can compute the input power from the output power. And imposing this power factor and knowing the voltage we computed, then we know the RMS value of this working point, and then the peak value. Yeah, here just to remind you that there is no limitation on the current supply, but usually from the specification we have to know this limit of current. So for our next computation, then we are going to consider this one as our maximum limit for all the working points. Yeah, then we had this drive specification. Then we need to start with the geometry, because if you start with flex motor, you need some inputs. We start a new project with flex motor. Yeah, just want to come back on the supply. I told you that we can impose here 600 volt DC, and then choose the right or the corresponding control strategy. This is what I did myself here in the computation, and applied this coefficient to take into account the voltage drop in the power electronics. Okay, so then for the initial sizing, we need for topology, we need these inputs. First inputs to start with flex motor, outer diameter, inner diameter, the length, number of slots, the air gap, the rotor diameter as well. As as well as the number of poles. So if we have, once again, we have some existing motor close to the specification we have, it's better to start with this motor and resize it. But if we don't have anything, so we have to start from white page. And you will see that starting with a white page will be a little bit difficult, and we have to fix a lot of parameters in order to get something to start with and to analyze. In our case, we are going to use the TRV, the torque ratio per volume. And here, once again, in the specification, there is nothing on the volume constraint. So it's really, again, harder for us. But anyway, thanks to this TRV, we are going to fix the diameter to obtain the length, or to fix the length to obtain the diameter for a given value that we are going to have. For this machine, I selected a TRV of 50. So this high performance servo motor. Okay. But as you can see, for this high performance servo motor, there is a big interval from 15 to 50. And actually 50 can be also an aerospace machine. So once again, there is a big interval here. So there are some tries to do here, try and make a computation. That's why we may have some iteration and maybe 10 candidates or more. But in this example, we are not going to test a lot of. So as I said, I will test 2 configuration only. Okay, so then I will fix the TRV as 50 kilonewton meter per meter cube. I know that from the output power given in the specification, I have the output power, I have the speed, so I can compute the torque. Okay. Then if I take the security factor of 3%, because 3% is due to all the assumption we are going to do, and maybe in order to cover some simulation or computation error. So this is something 3 to 5% are okay. Yep. So with this security factor, we are going to have this torque. Then, as I told you, from the TRV, I fixed the TRV. So the TRV is the torque multiplied by the volume, right? So then I will make a ratio between the length and the outer diameter of the rotor of 1.5. So this is something as well we can see often on rotating machine. So this is not unrealistic, if I may say. Okay, so then if I put this ratio, so I have a simple equation depending on the diameter, right? So only the diameter, knowing the torque and the output torque I need, knowing the TRV, so there will be only one unknown, which is the diameter or the length. So if I put the diameter as unknown, then I have just to put this ratio, and I have the simple equation. Then when I solve this equation, I will have a diameter of equal to 184, sorry. and the length of this machine is about 276. So D here is the outer diameter of the rotor, right? And then to find the outer diameter of the stator, so we have to fix a ratio on the usual ratio of the stator outer diameter of the rotor divided by the outer diameter of the stator is usually comprised between 0.5 to 0.8. Okay, so if we take 2/3 of this as a ratio, so then we will have this outer diameter of the stator. Yeah, so once again, as you can see, when we start from the white page, there are a lot of parameters like this to fix in order to get something to start with. Okay, then I have the length of the machine, the outer diameter of the rotor, the outer diameter of the stator. Then I have to fix the maximum length of the machine, including the end winding. Once again, this is the maximum length, or the stack length divided by the maximum length is a ratio between 0.5 to 0.8 as well. Usually, if I can okay. Yeah, usually if this is the stack length of the machine, then the end winding length is usually this is something equal to the half of the machine. You have 1/4 and 1/4 each time. So this is something we can see on the existing motors. Then we are quite sure that the maximum length of this machine will be 461 millimeter. Yeah. So then we have all what we need to start with flight motor. We have the outer diameter, we have of the stator, outer diameter of the rotor, the length, the stack length. So we miss only the number of slots, the number of poles, and the length of the air gap. Okay, so the length of the air gap, we are going to take it 1% of the outer diameter of the rotor, and then we have to fix the number of poles and the number of slots. Well, for synchronous reluctance machine, we said that we don't want to go more, to have a lot of poles, because it will degrade more the power factor. This is in one hand. In the other hand, the torque is directly proportional to the number of poles. So I don't want also to put only two poles, because I want to maximize the torque. So then 4 poles and 6 poles are good candidates. Then when I have the outer diameter of the stator, we will have enough place to have 48 slots. So here, if we make 48 divided by 3 divided by 4, so we will have 4 slots per phase and per pole. Okay. So then once we fixed all these parameters, Yeah, then we can start then with flex motor. So in flex motor, I will choose this one because I fix the diameter of the air gap, and then I can uh, I can fix the outer diameter of the rotor, the length, the number of poles, the number of slots, and I'm done. Okay, so let's do it. Maybe. Okay. Then in the next page, we will start with the stator. We are going to find the right winding. We are going to find the right number of turns later, and we are going to see try to find the right rotor. So let's come back to the stator. So if I go to the winding directly, the first thing I want to do is to find the right winding scheme. And I told you the right winding scheme is for me the one giving the high fundamental with the lower THD, lower harmonics. So how to test all this configuration? So I have to go to the winding and then go to easy. This is the best way to do. You can use advanced, but let's stay in the easy one. As you can see, with one layer in slot, you have only a possibility the full coil pitch or the shorter coil pitch, and then you can choose between lap winding or concentric winding. So for each configuration, please have a look on the spatial MMF, especially then the harmonics. Or you can export this table for each configuration, and then you can compare the fundamentals and the total harmonic distortion as well for each configuration you test here. But if I put 10 here, so I have this one. If I put 12, I will have quite the same thing. Maybe if I put 2 then and make a shorter, so then you have to test several configurations like this and choose the best one. Okay. Here in our case, I selected the configuration given automatically, right? So here, the first one. The second one is with the full coil pitch, 2 layers, lap winding. I put easy and B 2 layers and the lap winding. Then I have to look to my MMF and the table of harmonics. And the third one I selected here is the coil pitch with 11. Okay. And then I have to select the harmonics and to have a look on the tables. So let's compare them. Here, as you can see, configuration 2 has a higher fundamental, but harmonic 5 is quite higher than the other one, right? So if we look configuration 3, it seems the best one because we have this higher harmonics and higher fundamental and quite similar, at least fundamental, but smaller harmonics. So then let's see with this configuration 3. Something we have to pay attention because to not use copper for nothing. Yeah, we have this quite big hand winding. As I said here, maybe the solution is to increase the number of poles in order to decrease this hand winding length. But fortunately, if we increase the number of poles, there is a risk to degrade the power factor. So for sure, then we are going from this statement, we are going to continue with this configuration, 48 slot for pole, but definitely we are going also to test 6 pole and then 72 slot, because we still have room to put more slot and to have better distribution of the winding. Okay, so we'll continue with 4 pole and 48 slot, but we are going to test as well this 6 pole 72 slot. Okay, then configuration 3 of the winding is chosen here, and we are going to continue with it. So this is a configuration, a recap of the configuration. We will keep the same dimension, number of slots, number of pole, 48 per pole, 2 layers per slot. We have no choice to have this longer and turn. The winding factor is something I can read directly from the characteristics, and we have this winding factor directly given here. Yeah, let's continue with this one. And now what we need, still need on the stator side is to compute the number of turns for this machine. So the number of turns for this machine will be computed from the back EMF. And unfortunately, since there is no permanent magnet here, so there is no back EMF. There is a way to compute it from the different inductances in the synchronous reluctance machine, but it's a little bit complicated. So let's keep pragmatic and consider this machine as this stator of this machine as a stator of a permanent magnet machine. Then we'll use back EMF anyway to compute this stator. If you remember, we are not totally false because the stator of synchronous reluctance machine is similar to the stator of permanent magnet machine, and it's similar to the stator of induction machine. So we can keep this assumption without a lot of error, if I may say. But yeah, please note that there is another method, a bit complicated, using the different inductances LDLQ. That means that to compute the number of turns, you have first to compute the inductances, and then you have first to compute to consider the good rotor and so on, which is really complicated. So I prefer really to keep this assumption. Let's consider that this stator is a stator for a permanent magnet machine. Then let's use back EMF. Yep, so the back EMF, this is something we compute from Faraday's law, if you remember. And actually, if we develop the Faraday's law in dphi by dt, we will come to this function So this is a constant multiplied by the winding factor, multiplied by the number of turns, multiplied by the magnetic flux seen by one pole, and the frequency. So starting with the winding factor, this is something we have directly from flux motor. Then we are going to compute the frequency. We know the number of poles of this machine. We know the speed that we want to consider for the computation, 2000 RPM. Then the frequency is obtained from 60F divided by D. We said that the speed is equal to 60F, which is the frequency, divided by the number of per poles. So we can compute, we know the speed is 2000 RPM. The number of P of per poles is 2, so we can compute the frequency. Yeah, so then we have this winding factor computed. We have the frequency computed. We need to know to compute the number of turns. So there are still two unknowns: the magnetic flux over one pole and the back EMF. Yeah, so the back EMF we are going to target is the voltage supply we computed previously with drop voltage. So why we are doing like this? Because if we consider that this is the stator of a permanent magnet machine, to simplify, if I put a single phase, an equivalent single phase of the machine, this is a voltage supply, this is a back EMF, this is a resistance of one phase, and the inductance of one phase, right? So for 2000 RPM, I will produce this back EMF. I computed the voltage here previously. So I consider drop voltage of 0.9 due to the impedance of the phase. Okay, then for 2000 RPM, I will have this back EMF taking into account this drop voltage. So remember that the voltage we computed previously was a phase-to-phase voltage. We have to divide it by square root 3 to go from through phase-to-phase voltage to phase to neutral voltage. Okay, so then we computed the back EMF. Remain only the magnetic flux unknown, because TPH is the number of turns in series per phase I want to compute. So how to compute now this magnetic flux over one pole? It is computed through flux density on the air gap, and this is the geometric. So D is the outer diameter of the rotor. LSTK is the length of the machine. P is the P pole machine. So what does it mean? It does it mean I have this machine. Then I am considering this section. So I have this section. I have the length of the machine, the diameter of that I want to consider here, and P is per pole. So here the section is to cover 2 poles actually, because I have a 4-pole machine. So here as well I have to impose the peak flux density in the air gap. I will not make a lot of error if I put it to 0.8 Tesla. Here, the d will be my outer diameter of the rotor, and once again, elastica is the length of the stack of the machine. Okay, then I can compute like this the magnetic flux over one pole of the machine, and then I know the magnetic flux, I know the frequency, I know the winding factor, I know the back EMF. Then it's easy to compute the number of turns in series per phase, which will be 38 turns. Okay. But in flux motor, I need the number of turns. If I go here, the number of turns per coil. So I have to compute the number of turns per coil. So the number of coils per pole and per phase is have to divide the number of slots divided by the number of poles divided by the number of phase. I have the number of coil here per pole and per phase. So the number of turns per coil and per phase will be 2.37, which is very small actually, and it can lead to thick teeth because the slot will be smaller. Or I can put on mainly two turns and put a lot of wires in hand. So to avoid that, I will put the coils in parallel. So I have here 4 coils, so I will put 4 coils in parallel. So instead of having the coils like this, so I have to create another one. Instead of having the coil, so two here and 2 here and 2 here, I will put them in parallel. And here I will put 8. So if I have 1 volt here, 1 volt here, 1 volt here, 1 volt here, I will have 4 volt. I can have then 4 volt directly in parallel here. Okay. So if I put the coils in parallel, I can increase the number of turns by the number of coils in parallel I put, sorry. Then I can finally have, instead of 2 turns in series, I can have 8 turns in parallel with the other coils. So now I have the number of coils, so I can put 8, and maybe I have to play on the diameter here. So the slot filling, maybe have to put 10, and then once again maybe the diameters I have to choose one smaller. Okay, I have to put a liner and the phase separator. Okay. Yeah, so then I have my coils, I have my winding, I have to put 4 coils in parallel, right? And I am done with that. So now I finished with the stator, not totally, because I have to come back to the end winding, and since I know the maximum length of the end wind of the motor, sorry, and the length of the stacking, I can easily compute the length of the maximum length of the unwinding extension. But I will come back to it later. Now, which is the more complicated task here for synchronous reluctance machine is to find the right shape for the rotor. So from the indication we have seen yesterday, we said that there is an impact of the number of layers. There is an impact of the insulation factor, KWQ. There is an impact of the width of the bridges and the reels, and so on and so on. So there are a lot of ping pong to do here, and ideally is to start with this simplified one with 4 barriers. So if I come back to topology here, okay. So here I have like 1, 2, 3, 4, maybe 1, 2, 3, 4 barriers can be okay. Yesterday we have seen, on the example we have seen yesterday that 3 barriers or 5 barriers are better than 4 barriers, but in our case we have to test 4, 3, and 5 maximum and see which one is the best actually. If I go back to the silency, right, we have to always look on this coefficient, which is the insulation factor, which is, I think, the most important one. So I advise you to start with this simplified one, because you don't have a lot of parameters. So here I will select radial. I go here. So it's called EVR RFB. EVR radial C3. And it is A04. Okay, and then here you have really not a lot of parameters to play with, and each time you have to have a look on this insulation factor, which is again should be equal or close to 0.86. Then we said that here maybe we have to put 1 millimeter at least maximum, and what is it? The bridges here, maybe it's we said that it should be something like 1 millimeter, and then maybe something we have to take care is to not saturate these layers. So ideally we have to look to the stator tooth, and maybe here we can put larger maybe we can start with 4 or 5, and keep an eye on this KWQ. It's not an easy task, right? You will have a lot of ping pong to do before having the good one, which is close to 0.6. Once you have the good simplified shape, yeah, you can then have a look on other topologies because you have already an idea about the diameters or the dimensions you need to do. In my side, I started with this one and then moved to this one. Why? Because this one is the one I have seen that follow the best the flux lines actually. So how to get this flux line? One needs to make a fake IPCN test, right? Just once you get here in the silency something close to 0.6, yeah, then you have to launch a fake IPCN test in order to see the saturation and to see the flux line. So yeah, you need to make this fake IPCN test and have a look on the saturation. Let me once you have this fake test performance, please have a look on the inductances. The flux densities on several locations, the stator tooth, stator yoke, rotor yoke as well, and we have to know that all these flux densities in the air gap on the stator tooth, there are some intervals that we need to respect for the flux densities. The initial test I made, the flux densities were okay for the rotor, but a bit saturated for the stator. So what I did is to make the stator a little bit bigger. So instead of 276, I put 300 now. And with this new diameter, I can see that my stator yoke is less saturated than previously. Remember that, once again, synchronous reluctance machines are very sensitive to the saturation and the number of poles. So the power factor can be really degraded due to the saturation. So this is what I want really to avoid by enlarging a little bit the stator. Okay, so by far this is the rotor shape is the biggest issue here, and this is the step where you are going to spend a lot of time. You can use optimization, for instance, at this first level. So couple flux motor to hypersteady and launch a parametric steady in order to reach this KWQ equal to 0.6. Or you can make it as I did here, just make some ping pong and you are done. Okay, so here maybe can make 20, and then once again maybe make 6, and here make 6. You can see it, this is already something I start to be close to what I need. Yeah, so here it seems something good enough. I have 0.63 as a factor. Then I can imagine to start with this candidate, and before moving to more complicated one. Okay, so then once again to estimate the saturation, one needs to make this fake initial IPCN test in order to see the ISO values and to see the ISO lines of your machine. So let me open it. Okay, so if I go to the initial sizing, we can see the ISO lines, you can see max density, and so on and so on. Okay, then once this big step finished, yeah, then you have all what you need, right? You have the starter with the winding and so on. We can now come back to create a new project, a new candidate, and then start your analysis. So what you have to do is, because you have already the shape of the rotor, you can keep the material you choose and the part library for, you don't need to use it because you have enough shape for the rotor and for the starter to start with it. Yeah, so then you can always go to the motor directory, here, motor catalog, create your own catalog. Here I created this catalog for the training, where I put all the candidates I want. So this is the best practices to have. So in your catalog, you have to create a new motor. I call it config 48 slot for poles, and then you can start with it. Okay, so the first thing is after the topology, the diameters and so on. Remember that the diameter, the outer diameter of the starter is now 300 and not at all 276. Why? Because we have seen that there is a big saturation on the starter yoke. Then on the rotor, we can use the one we found previously, or you can use the one I am using here. Okay, with all these parameters for the rotor silencing. Then once we finish the rotor, we have to move to the starter. So we have already find it here. Find the right starter really, because we don't have a lot of saturation on it. So the tooth dimensions are okay here. So we will consider these tooth slots, parameters, and continue with our winding. We are going to select Y connection, use easy mode with 4 parallel paths, and shorter coil pitch, as this is the best configuration we found previously. Then we have to go to the coils here. Come back here, coil, and then we have to indicate the number of turns, the number of wires in hand, and the insulation, and we have really the view of the slot filling here to choose the best one. Once you finish the slot filling, you can have a look on the characteristics for to see the fill factors, to see the resistances here, the phase resistances and the end winding and the masses. Okay. But we still not finished really the end winding, because remember that the end winding we computed the maximum extension or the maximum length of the machine. We know the length of the stacking on the starter and the rotor, so we can compute easily this extension. Actually, here I have a maximum extension of 92.5, and to compute this minimum extension, I can have an idea about I know the diameter of the wires I am using, and now I knew as well the number of wires and the number of slots I have per phase, so I can compute this width, the width of the end winding, and then I can compute this smaller value thanks to the width I estimated and the maximum extension I computed. Okay. Then once you finish your winding, you have to go to the materials. I'm going to use this material for the rotor, the same material for the rotor. I am going to use the copper as well for the windings. Something interesting to have a look as well on the windings. Once you finish the end winding, you have already the masses, the total mass of the copper you are going to use. Right, so electrical conductor. So in this machine, I am going to use 26 kilograms of copper. Yeah, so I have finished the materials. Once I finish the materials, now it's turn to make the test. So the first test I am going to do is sine wave performance mapping. Sine wave performance mapping is here, so you can go here. And what is interesting for me is there are 2 points indicated on, if you remember, on the specification. I need at 2000 RPM to have 75 kilowatt and the maximum speed of 3000 RPM. So for this test, I have computed already a current previously, if you remember. So we said that I will consider it as a maximum current. Okay, so I can put it here as a maximum current 200. For the thermal, I don't know yet the thermal behavior of this machine. So I will just fix some temperatures on the active part of the winding and the end winding. Here I am going to use directly the DC bus voltage I have from the specification. So I will use 600 volt. Here it's kept circle, but you have to modify it to 180 6-step. Yeah, then I am going to use a command mode MTPV, and the maximum speed I am going to impose is 3000 RPM. Yeah, once again, this is the maximum speed I want to reach. Okay, then once you launched the computation, or maybe before launching the computation, you can add the mechanical torque here, because this is the working point at 2000 RPM. So here you can add your duty cycle or a single point here. So I want to have 369 with a security factor at 2000 RPM. And then you have to select the command mode. We have only 2 command modes, MTPV, maximum torque per voltage, or maximum torque per amps. I'm going to choose the maximum torque per voltage, and then, okay, launch the computation. So once you launch the computation, you will have the results, the envelope, the torque, current, so on, and the efficiency. Here I think it's not MTPV I have here. If I go to the settings, inputs. Yeah, I launched the computation MTPA, so it's good to have it here, so you can see the difference between MTPA and MTPV. Yeah, so and you can see in as indicated here, the MTPV here is the result with MTPV, and here is the result with MTPA. In both command mode, I have my working point target here. And actually, you can go to the user working point, which is at 2000 RPM. This is the one specified in the specification. So this machine can definitely give us this torque at this speed with quite good efficiency. So this is what I am looking for. So you can have all the curves and the user working point we have tested. And you have to look at the current, actually, the efficiency, the power factor as well. Here, remember we fixed the power factor of 0.75. Here we have a lower power factor of 0.73. So I am happy with this machine, and now I want to make some additional computation in accurate mode in order later to have iron losses on the rotor and to have a look on the torque ripple as well of this machine. And with this accurate computation, I can make later accurate thermal computation. So if you go to sine wave working point here, since you have the current, right? You have the control angle, you have the speed, so you have all what you need to make to perform IPCN test. So the IPCN test, you have to go to the sine wave working point here, select IPCN test, and then same thing, put the temperature you think that you are going to reach, at least the maximum temperature allowed for your winding, for your thermal class of your winding, and then perform the computation with that. So you have, once again, fast is using mixing method Park and finite element, or accurate, where you can have flux 2D behind running. Okay, so this is what I am going to do here, is to use IPCN test to impose the temperatures and select accurate. So the current here is the one I computed previously. The control and the control angle I computed previously, and I can then compute the accurate mode. I don't include AC losses because the speed is not too high, but it's also possible to include the AC losses in our case. Okay, so this is what you need to do. Then you have to put the temperatures here, select accurate mode, impose the current you computed, the control angle, the speed, okay, and you have to launch the computation. Once the computation are finished, then you can access to the torque. Here with accurate mode, which is pure finite element computation behind, I have 360 Newton meter, and previously actually with a full Park model, mixing analytical and finite element, I have 369, right? So lower torque, but no problem. It's still what I need because I can develop 75 kilowatt for this machine. Okay, so and we have to look to the current density. This current density is a good indication actually on the thermal behavior. More the current density is high, more the thermal constraints will be hard, and there will be joule heat to extract from the machine and to cool the machine. So 6 amps per millimeter square is really good. And the power factor, as you can see, is more or less the same as previously, with a really good efficiency so far. Then the other drawback of synchronous reluctance machine is really the torque ripple. And we have here like 12% of the torque ripple, which is a little bit high, but there is a room of optimization. It is still possible to reduce this torque ripple and keep the good performances for the machine. Yeah, so this machine, this configuration candidate is okay from magnetic point of view. We have to make the thermal computation on it, but we said that the current density is really good, so we may expect a good thermal behavior of this machine. Then the torque ripple is a little bit high. Yeah, it may lead for vibration. Not always the torque ripple is equal to vibration, but in some cases it can be the source of vibration actually. But anyway, a torque ripple, if you have a gearbox, it will be transmitted to the gearbox as well. So here as well, I am not afraid because we can make some optimization to reduce this torque ripple. Yeah, so this is from electromagnetic point of view, this machine is a good one. So let's now test the other machine in order to reduce the end winding. So we said that we have to increase the number of poles and then increase the number of slots to have a better distribution of the winding. And we said that we have a big diameter, so we have room to put more slots. So let's test this one. If we change the number of poles, then we have to have a look again. So we have to make some ping pong in order to find the right shape of the rotor. Keep in mind that this insulation factor should be close to 0.6. So you have to make this work. And then, since we are going to change the number of slots and the number of poles, we have to make a computation first of the good winding. Then we have to make the same work in order to choose the good winding configuration. So we have to look at the MMF and choose the right one. Once we had this, we have to keep more or less the same width of the stator tooth. Then it means that we will have smaller slots, but it's not a problem. So then we need to compute once again the number of turns. We have to make the same work as previously, the same strategy. We are going to consider that this is the stator of a permanent magnet machine, and then make a back EMF test and the back EMF computation, and compute the number of turns, right? So here the number of turns will be 12 with six parallel paths. And we are done. Then we are going to make the test. So once again, since we are going to change the number of poles, you have to make some ping pongs in order to choose the right the right shape and to keep the right insulation factor KWQ. Okay, so we have this machine, and then same thing. The first test we are going to do is to go to sine wave test, performance mapping, impose maximum current, choose the MTPV command, maximum speed, indicate our working point, the target. This was indicated in the specification. Before that, in the settings, put the temperatures, at least put the highest temperatures we have for this winding, the thermal class of our winding. Then we launch the computation, and you will see once you launch the computation, unfortunately, the working point is outside outside the efficiency map. That means that the configuration we have now will not satisfy the specification. If I come back to this, we said that we can play on this shape of the efficiency or the contour of the efficiency map. So to move this point horizontally, you need to play with the number of turns, or to play with the length of the machine. And if you want to move to have more torque vertically, then you have to modify the current supply or the current density. That means you need more current actually. So to have more current, this is also possible to achieve it with a higher number of turns, right? So there is a compromise to find about between the number of turns and the current supply. In our case, what we are going to do is simply to play on the number of turns. So here we have really a higher torque, right? But we need to decrease the number of turns. Why? Because with the number of turns we computed here, actually we have more back EMF. That's why we cannot make like a flux thickening here. So then we are going to decrease the number of turns to push this point in the right direction, and then decrease the torque. So if we move to 8 turns, so it's not decreasing here, but increasing the number of turns. So we are going to increase the number of turns, and then this torque will decrease. And with this configuration, because if we increase the number of turns, you have to modify the number of wires in hand, otherwise you will not be able to fill the slot. Once we did that, with this new winding, we can see that now this machine can reach the working point and can reach the maximum speed of 3000 RPM. So with a relatively good efficiency, but unfortunately with smaller power factor. Okay. Anyway, we are going to do the same thing. So as previously, so we are going to use this control angle, use this speed, and use this current, and make a computation in accurate mode to see really the torque ripple of this machine, of the 6-pole machine with 72 slots. So if I go to working point here, and then select accurate mode, put the temperature as previously, and impose the current and the control angle and the speed we had previously, Then we can launch this accurate mode for this working point. We can see that we have better torque, more than what we need actually. Quite good efficiency, all right? But unfortunately, we have increased the torque ripple. Yeah, so then both machines satisfy the specification, but we have now to make a choice. So what we are going to do is to compare the two machines for the working point specified from the specification. So first, the power factor is better in 4-pole. Then the weight. Here, 4-pole, 6-pole. We have the total of 26 kilogram for the winding, and lower winding, lower copper in 6-pole. The wool motor is 125, so it's higher in 4-pole than in 6-pole. So what I did as a comparison is to keep how many good points we have in each machine. So when I compare the two working points, 4-pole machine, I have better efficiency, 1 point. I have better power factor, 2nd point. I have better or lower torque ripple, and I have lower current density, right? So whereas in 6-pole, it has only 2 good points, lower weight and better torque. So this is my configuration, but my comparison, maybe you want to have cheaper machine, and you don't take care about the points I need here. So if you need a cheaper machine, then the 6-pole is better than the 4-pole. So depending on your way to compare, you will have best one. From my side, I choose better efficiency. I choose better power factor, because this better power factor will have an impact on your power electronics. So you will have lower losses on your power electronics. So for me, definitely I choose the efficiency more than the price of the machine. Okay. Yeah, so then we will continue with a 4-pole machine, right? So a 4-pole machine, I need now to be sure about its thermal behavior, because I may have a really good machine from magnetic performance point of view, but it will, from thermal point of view, it will be overheating. So in flex motor, I can make some thermal computation. Remember that in the specification, there is no indication if we are going to make water cooling or forced air cooling or something like this. So it's up to us to choose the right one. So this machine, I will just save it as here and make duplicated. So to duplicate a machine, once you save it, you have to select it here and make duplicate in order to make a thermal computation on it. Why? Because when you make modify the geometry, you will lose your results. So in my case, I save the results here. For each working point I did, I save it. But when you modify the geometry, if I go to the housing, and then you select to make a housing, if you have current results and you didn't save them, they will be deleted. So that's why I advise you to create another or to duplicate the machine, to save first the result and then to duplicate this machine in order to add the thermal computation. So when you duplicated it and you save it, here I choose to just simply indicate thermal. Then you have to go to motor factory, design again, and add your housing. And this is the dimension of the housing I want to add. Then add the fields. So always in the same location, you can add the field like this. Then you have a choice between parallel or radial fields. Okay. Then here we choose these parallel fields and choose this configuration with these dimensions. I have radial and axial view always in Flex Motor. Then you have to add the shaft, because from thermal point of view, there is a thermal conduction axially. And then you have to, of course, make the right dimensions, and then add the bearing. If you have some mechanical losses, this is the location of the mechanical losses. They are located in the bearing. Okay, so then the shaft and the bearing with these dimensions I selected. And you have to go back to the winding in order to add the impregnation. So you go back to the winding here and go to, you have, this is something, you have a potting possibility to add, really. Can make a potting or not. But in my case, I need to add the impregnation. So here I have to put yes. The impregnation goodness, I would let it to 90%, or in the example we said we have to move it to 80%. Okay, then you have external cooling, right? External cooling, you can choose first natural convection or forced convection. Okay. And if you choose, in both cases, you have to indicate how is the machine oriented? Is it horizontal? The cooling is from the up or here. Okay. Then if you have a flow, a forced flow, from which side? In our case, we made the forced cooling, and we make a ratio of 1 speed. So the speed is considered for the cooling is the same speed of the machine, of the rotor speed, and we choose the altitude of 300 meters. Okay. Something interesting in Flex Motor is that when you make these cooling characteristics, you have already some results. So about the natural convection, the forced convection resistance, forced convection coefficient, or radiation, right? So this is externally, and you may it can be interesting to have them if you move to Flex in order to make a computation, thermal computation directly in Flex. Okay, then once you finished the internal characteristics of the cooling, external, sorry, then you have to move to the internal. So the internal, as I indicate here, let's try first without any cooling. So we will keep it only natural. Okay. So with this design now, we can go to the test. Yeah. Since we added something, we added some components like the housing, the shaft, and so on. Then we have to choose the right material. But now you can have the housing with aluminum, for instance, and the shaft with iron. Yeah. Then you have to choose the right materials. Here for the housing is aluminum. Shaft and bearing, we choose this iron. Okay. Yeah, so we will see then the results with the forced cooling. Then we are going to make a thermal computation, a steady state thermal computation. Once again, there is no indication on the running services in the specification. So we consider that the working point is a continuous working point, and then we can go to the thermal and choose steady state thermal computation. Here, since we had already some computation done for this machine, we can simply go to the import and import the results of this the working point we did previously, and it will be imported. Yeah, there is no mechanical losses, otherwise we can import them from the previous test. Mechanical losses for all the tests we are going to do, they are inputs. They are not computed with the flex motor. Okay, so then you can put some mechanical losses on the bearing, but honestly, I don't have any idea about the amount of mechanical losses for this machine. I put this value just a small value just to include some thermal, some mechanical losses on the bearings. Okay, then once you have your settings with ambient temperature, which is 40 degrees, you can launch your computation. And then when you launch the computation, you can have the results of your machine like this. So you can have the view, the temperature distribution. As you can see, the maximum is on the unwinding, which is 140 degrees, which is really acceptable for us, and we can consider it as a good thermal behavior. Then you have this table, final temperature table, which is giving you the temperatures, the mean value of the temperatures on each location of the machine, the shaft, the bearings, the rotor yoke, the stator yoke, and so on. Yep. So this is let's say load this one. Maybe I will open directly the thermal one. Yeah, so this is the steady state computation, but in flex motor we do have an iterative thermal computation. So iterative between magnetic and thermal. So this is maybe the best analysis to do. Then how to do that is once again to go to sine wave test, and we are going to consider fast because the iterative and the accurate one is pure finite element computation, so it's a transient 2D computation. It may be really long computation. Here, in this iterative working point, we are not going to consider the iron losses on the motor. We are going to start with these temperatures as initial temperatures or this working point. If you go here, sine wave, IPCN, thermal, you can then choose iterative like this. Okay, so once you choose the iterative, then you can put the previous current, control angle, and speed. You can include the torque ripple if you want. And then you can launch the computation in fast mode once again. And then at the end of the computation, you can access to this view as well. We can have a look on the temperature distribution, radial view, and axial view, and you have then the table, the recap of the temperatures on each location of the machine, and the working point with thermal iterative computation. We still keep the same performances as previously actually, which is quite good for us. Yeah, so the conclusion is obvious, if I may say that, because really the maximum temperature here is 107 degrees, so we are far from the maximum temperature we used to see for the windings, like 180 degrees. So we can say that with this condition, with this cooling, this machine can run continuously without any problem. So once again, the torque ripple was 14%. There is a room to optimize it. Can make a couple flex motor to hypersteady and make the optimization. There is also what we call shape optimization. It's a new optimization within Flax. It can help to optimize the torque ripple and keep the performances of the machine as the initial one. So now let's see about the NVH behavior of this machine. So as previously, save all of the thermal results and then duplicate the project in order to make some NVH analysis. So you can see you can have three separate projects, magnetic, thermal, and NVH as I have. Then to make a test, NVH test, you have to go to NVH, and we can make first the IPCN test. From the specification, we have two working points, one at 2000 RPM and the other one at 3000 RPM. So I may test this motor only for these two working points, or if I have like a duty cycle, or I can also test it. So if you don't have the duty cycle, you can have a spectrogram for the envelope of the efficiency map. So once again, the NVH computation is mixing analytical computation. So the analytical computation is mainly used for the frequency, the natural frequency computation and radiation efficiencies for the motor. So the motor will be considered, because it's analytical, we have to simplify it. The stator mainly will be considered as a ring in order to make easy to compute these natural frequencies. And then the magnetic pressure or the magnetic forces are computed behind, thanks to Flax 2D, which is a full finite element computation. and then this is what will take time actually in this NVH test. Okay, so to make a test, let me maybe open the NVH one. So to make the NVH test, here we are going to start with the IPCN test. So only one working point. Then you have to make the thermal settings. So working point, thermal settings. Put the temperatures you compute previously, and the current, the control angle, and the speed that you want to consider. Here, in our case, we are going to consider the working point, the 2000 RPM. And then you will access to all these results. Let me show them. So, natural frequencies, the radiation efficiency, this is something computed analytically. This is something we computed through Flux 2D, which is the finite element computation, Maxwell pressure as well. This is another view of the Maxwell pressure. This is a WFFT of the Maxwell pressure. But honestly, what is interesting for me, for this machine, is really the overall sound, the noise of this machine. Is the machine noisy or not? So I want to see the overall sound power level, especially with this dBA. So we have here like 56 dBA, and if I continue the work with the 6-pole, it can be another comparison point here. Maybe this is something you can do in your side and compare which machine is noisy, 4-pole, 48 slot, or 6-pole 72 slot. So this is something you have to do, maybe, or homework for you guys. Yeah, you have already several results, but the most interesting one for me is this one. And then the other test we can do is the spectrogram. This is an additional test because once again in the specification I have only 2 poles, but let's consider the spectrogram, right? And let's consider the envelope of the efficiency map. So to do that, once again you have to make the temperatures or we computed temperatures previously, right? The electronics is as previously put 600 and put 6-step here. And then you can go to the, sorry, you can select the torque speed envelope. You can impose the maximum line current and the maximum speed of 3000 RPM. Okay, once you did that, you can launch the computation. You will do not be surprised because the computation will be higher in this case because it will first compute the envelope of the machine, torque speed, and then each working point will be launched in transient, Flux 2D transient computation. And at the end of the computation, you will see that there is a comparison between the Park model and the transient, pure finite element computation. So we can see that there is a good agreement between Park model and the pure finite element computation. For in the flux weakening side, maybe the machine starts to be saturated and we start to have a lot of harmonics, then the transient computation, there is a deviation between Park model and transient computation. Anyway, for our NVH computation, this is the transient finite element computation will be considered in order to compute the magnetic forces. Okay? Then, yeah, you have a few interesting results here and a few interesting results from NVH results. Once again, like for one working point, you have model analysis, radiation efficiencies. This is something computed analytically. And then this is something where we mix analytical computation and magnetic pressure computed from flux study in transient magnetic application. Yep. What I need to have a look on it is, for me, as a designer, is really where the machine is noisy. I can say that we can have here some resonances. Let me have a look on the working point at 2000 RPM. It's 67 dBA here, but fortunately we are not in this working point where we have this resonance. So in lower speed we have higher noise, and maybe you are fortunate to have this working point here, and we can expect that for this machine it is called synchronous reluctance machine. So as for the switch reluctance machine, more you go on higher speed, more the machine is noisy, unfortunately. So for 3000 RPM, the machine is really noisy compared to the continuous working point. So yeah, once again, this is a good comparison point to have when you consider several configuration, like we did today with one machine with 6-pole and with one machine with 4-pole. Maybe it makes sense to make as well the study for this machine with 6-pole. Okay, right, then I am happy with all these results actually, and then once you finish the results, you may choose to make optimization, then you have to export to HyperStudy. You may want to make some shape optimization, then you have to export to FluxStudy. Or you want simply to have a report, then you can build your own report where you can add all the design topology, all the tests, the material characteristics. You can add all the tests you saved, and then yeah, you can generate your report as a PDF format and export it. So you will have all this information inside actually. Okay, really a complete report for your own usage. Yeah, so I told you that there is a room for optimization. You can make a really magnetic optimization, or you can make magnetothermal optimization, or magnetothermal and NVH optimization. But the complexity will increase with adding other physics. So I put here a link just to have a look on what is possible as optimization. So this is really something you can drive through hyperstudy, where you can really put a lot of physics and make a complete multi-physics optimization. So this is what we call at the end parametric optimization. There is as well what we call shape optimization. Then you need to export to FlagStudy. And the shape optimization, I put here a link to the video. Here, how to use the shape optimization in order to reduce the torque ripple and keep the initial torque or the initial performances of the machine. We go to the end. So the shape optimization, it's not the parametric optimization. It will use the mesh, really. So it makes the life easier for you. But it's a really good feature because it optimizes the magnetic performances. Here we wanted to reduce the torque ripple and keep the initial performances. And in the last version, 2023.1, the one will come soon, is really including the mechanical stress on it. Yep, and by this, for me, this is the end of this example. I hope that you will make it or redo the example from your side and make the full magnetic, thermal, and NVH analysis. And it's up to you now to play with some equation and to play with flux motor. Let's have we have now room for question. Maybe the first question is from Ramin. Hello. So thanks, Ramin, for your question. Will it be possible to send me training material from PM motor design? Well, the PM motor design is in March. I invite you to subscribe. So I will be happy to send you then the training material. Then I have a question from Oscar. Can we export NVH analysis or force map into other Altair software like OptiStruct, for instance? No, from Flux Motor directly, no, but you have to go through Flux, and Flux, there is a possibility to link mechanical mesh imported from OptiStruct to Flux and make this NVH analysis. Yeah, so OptiStruct is really interesting because here we consider the stator and we simplify the stator as a ring, but actually the stator of the machine is not a ring, especially the housing with its really complex shape, and we may be surprised to have a shift of the resonances and so on. And I have a question from Ramin. Not synchronous reluctance. I want to learn how to design a conventional permanent magnet motor from scratch, including analytical calculation. Yeah, once again, Ramin, please come to the next training on permanent magnet machine design. It will be on March. Yeah, it's very late on March. I am sorry, but this is the schedule. Oscar said, can you recommend other sources to get more practices with motor concept? Maybe on permanent magnet machine, there is the book from Team Hendershot. This is already a good book. to learn on how to design permanent magnet machine. I'll say again about NVH, is it possible to take into account the right PWM frequency to know the noise results? Not in flux motor, since all the computation are done in sinus shape, but coupling flux 2D or flux 3D to OptiStruct, here you can do it, yeah. Can we import the 3D geometry in Flux? In Flux, yeah, you have possibility to make a 3D computation as well as 2D or skew computation. Another question about thermal analysis. If I do not have housing, is it possible to simulate it with any trick? For example, a housing thickness close to 0. Yes, yes and no, because unfortunately, if there is no housing, only way is to move to Flux, honestly. But what you can do is to compute the different convection coefficient within Flux motor and then use them in Flux 2D. Okay, good. Okay, thank you very much. Interesting question. Really happy to see all these questions. All right. If there is, if you don't have other question, really thank you very much to stay and to follow this training, even if it's for in the evening for some of you, or maybe early in the morning for some of the others. So thank you very much, guys, and yeah, there are other trainings, and the other one will be in March. Thank you very much. Thanks, Guillaume. Thanks a lot, Slavomir. Thanks a lot. Have a nice evening. Have a nice day, and so on. Bye, guys.
คุณเป่าแล้วคุณรักษากดจริงๆกับโดนด่าคุณเลือกแบบแต่ไม่ได้บอกว่าซ้ายขวาเราจะไม่จะรับเหมือนทำรูปกับหรือท่านอะไรอย่างเงี้ยเขาบอกผมยังไงผมต้องเลือกสิ่งที่มันถูกที่สุดแม้ว่าคนดูจะไม่รู้กติกาก็ตามแต่จะโดนก็ถูกต้องเลือกอะไรอย่างเงี้ยครั้งหนึ่งสมัยที่อยู่รอยังแบบเป็นดาวรุ่งขึ้นมายังไม่ได้มีชื่อมากไอ้ลูกบางลูกคุณถ้าย้อนกลับไปมันมีไม่ได้แล้วลูกบางลูกที่เป็นลูกถูกโทษไม่ถูกโทษเขาก็ทำตามสิ่งที่เขาตั้งเรียนมาถ้ามีอุปกรณ์ก็โดนนี้นะเขาเพื่อนแต่ไม่เป็นรู้ที่แต่ว่าอุปกรณ์รักษาในสิ่งที่เขาต้องการไปไม่ได้เขาถือวิธีการดีซ่าเอริกวิธีการดีซ่าเอริกเขาต้องการไปถ้าการทำไม่ได้อะไม่ใช่แบบคือเป่าให้มันเป็นปัญหาอยู่เรื่องไปว่านไปอะไรอย่างเงี้ยที่แบบผมไม่ได้พูดใช่เลยผมพูดแล้วเอาหมดแล้วเอาแล้วก่อนคือเอาอย่างนี้ผมบอกเรื่องบริษัทนักฟุตบอลไทยเลยว่าทำไมอุปกรณ์ถึงเป่าแล้วไม่ค่อยมีปัญหาโอเคแล้วมันอาจจะมีบ้างแบบใครจะไปตกเขาตกที่ไหนแต่อุปกรณ์ทางอุปกรณ์ฝ่ายนักเตะคนครับถามว่าอย่างนี้จ้าคุณคนนี้เพื่อนอุปกรณ์เขาอุปกรณ์บอกอธิบายอะไรทำไมแบบไม่เดินไม่แบบอะไรไล่อย่างเงี้ยฝรั่งอะไรก็ทุกครั้งก็ตัดสินไม่ได้เขาต้องเกิดทางแบบอธิบายแบบเขาต้องเกิดอันดับโลกตอนนี้การเวียดนามนะครับก็ดูผมเรื่องนี้ก่อนครับเพราะตอนนี้เวียดนามแพ้3 เกมรวดนะแค่แต้มไม่บวกแต่ว่าถ้าพรุ่งนี้ผมมองคือตอนนี้เราก็จะประมาณถ้าตัวคูเนี่ยประมาณอันดับโลกอันนี้คือไม่เป็นทางการนะครับก็เรื่องพอเขาก็มันเขาก็แข่งด้วยแล้วก็เป็นเวลาเรื่องที่ขยับประมาณนี้2 โซนเพราะฉะนั้นเนี่ยมันก็อาจจะไม่ได้ถึงขั้นที่จะเป็นแบบเอาแต่ถ้าไม่มีเราสมมติว่าเรื่องการมองอีกนะมองตาเลยที่บอกว่าแซงแล้วเพราะว่าวิ่งทางร่วมเหรอเราวิ่งทางไม่ได้เรื่องคือแต่เดี๋ยวมันรอก่อนนะคือเดี๋ยวที่แบบนั้นนะเราคิดว่ามันทำอย่างมีที่เหมือนกันมีเรื่องว่ามันคำนวณได้แหละเราก็ว่าแต่ว่าเราไม่ได้บอกว่าจากที่เขาคำนวณผิดเราครับคือเราไม่เชื่อก่อนอะไรอย่างนี้เราไม่ได้แบบที่ไม่อยากไปต่ำก็ไม่อยากไปแบบนั่งคำนวณแล้วแบบผิดตรงเนี้ยเรื่องนึงก็เป็นสิ่งที่เราเลยแบบเอาประมาณนั้นแล้วกันแล้วก็เป็นเรื่องการบ้ากันระหว่างทางด้วยแต่ว่ามีโอกาสแต่เราไม่อย่างนั้นคือถ้าสมมติว่าคณะซาอุในวันพรุ่งนี้นะครับถ้าเกิดหรือว่าไม่ชนะวันพรุ่งนี้แล้วมันต้องเกิดทีกันมันก็จะถูกกันมันมีโอกาสที่จะได้แตะเลข2 ตัวผมก็จะรวยกันโอ้ยที่มาเยอะเดียวแต่เลข2 ตัวนี่มันมาเร็วรถดีๆเนี่ยแกก็เลยบอกว่าอันนี้จะมาเป็นมาตลอดประมาณนี้ครับแล้วมันก็รอมาถึงมันเป็นสรุปก็เป็นเดือนอย่างที่ทราบเลยโอเคพูดถึงเจ้าตัวสี่ตัวที่สุดมันเรียกว่าตัวเป็นตัวอยู่แล้วเนี่ยผมก็ยังงงอยู่ที่ไหนผมก็คุยกับคนรู้จักพวกตัวที่สุดเขาก็ตั้งคำถามเหมือนที่เราตั้งคำถามที่เราตั้งมาก็เป็นตัวที่สุดแบบนี้แล้วแบบประตูญี่ปุ่นมันดีกว่านี้ด้วยนะแต่ว่าไม่ใช่อย่างเงี้ยผมก็เลยเป็นการแต่ผมว่าไม่จำแต่ไม่ได้ก็ไปเรียนกันเอาไปแล้วก็ไปเรียนกันมันไม่ได้เหมือนกันทำไมการดูอยากได้น่าจะเพราะใช้โอนาน่าเป็นครับผมไม่รอแล้วครับผมจะบุกเวียดนามนะครับผมติดทีมเดี๋ยวเดี๋ยว เราจะพูดเรื่องอะไรกันเกิดจะได้แบบมองครับอ่ะถ้าเราเข้ารอบเป็นที่สองที่จะรูทเดย์เนี่ยหรือเป็นที่สามที่ถ้าเราเข้ารอบเป็นที่สามเจออิรักเนี่ยเราจะเข้าเตะวันจันทร์แต่ถ้าเข้ารอบเป็นที่หนึ่งเข้ารอบเป็นที่หนึ่งเราเตะวันอังคารเราจะเตะอาทิตย์ก็เมื่อกี้เตะรอบที่หนึ่งครับผมขอบคุณมากเลยที่ติดตามกันนะครับขอบคุณที่คนที่ซัพพอร์ตกันนะครับก็ไม่มีอะไรให้ที่บอกว่าจะฉลอง50,000ก็มีแบบต่างๆแถมรับทุกเนี่ยเราจะมาลุยกันเลยผมจะเชิญทุกไปที่มีส่วนดีส่วนที่มีส่วนดีแบบที่มีแบบแค่อย่างเงี้ยเรามีปาร์ตี้เล็กๆขนาดความสำเร็จในบ้านปลายที่ของผมงั้นขอขอบคุณทุกคนเป็นประจำเลยนะครับที่มาดูเรื่องของความสำเร็จครับก็หวังเราคือแบบไม่ต้องมาแต่ต้องทำมันยากต้องกดตับแต่กดครั้งเดียวพอพวกเดิมไม่ต้องกดหลายครั้งกดให้กดแล้วถือว่ารับให้กดอีกทีนึงถือว่าเปลี่ยนแล้วไม่ถือว่าเดี๋ยวนะเราจะมีแบบทีมได้ทีเดียวก็เป็นแบบเป็นเป็นอาจจะเป็นความเด็ดเล็กๆก็ดีใจเลยครับเล็กๆเหมือนที่ไทยทำอย่างนี้ได้ดีงั้นให้ที่จอมที่จะลงมาแสดงว่าวันนี้ปีหน้าจะไปทีมแต้มสามแล้วก็ขึ้นมาได้รู้ที่ตูเขาได้ขึ้นมาเลยทั้งที่นะเราเนี่ยจะต้องมาโอเคไม่ต้องทำอะไรแล้วโอเวอร์อย่างเดียวเลยนะครับผมนี่นะครับขอบคุณมากที่มีรายการเราทุกก็ขอบคุณมากด้วยที่มาแชร์กันเจอกันวีคหน้าเนาะวันพุธเดี๋ยว3 ทุ่มเจอกันมาไม่ต้องมาหรอก3 ทุ่มเป๊ะเลยมั้งมาเจอกันวันที่หน้าโค้ชทีกับทุกคนที่นะครับเป็นคนที่ได้ครับตอนนี้เขาจะโดนรอบที่6ทีมนะอาจจะเข้ารอบหวังแต่ว่าคงไม่ได้ลาไปก่อน